Subscribers to In the Beginning receive carefully researched ebooks, detailed videos showing real DIY woodworking projects built step by step, and access to exclusive timber-related content not available elsewhere. This channel focuses on the subtle, often overlooked principles of wood behavior, historical craftsmanship, and material science that shape long-lasting construction. Many modern builders assume that structural integrity comes from strict adherence to codes, formulas, and uniform measurements. That assumption is only partially correct. Codes are designed for predictability, efficiency, and safety under typical conditions, but they ignore centuries of empirical knowledge passed down by old-world carpenters. One of the most overlooked aspects is beam sizing. Misunderstanding it doesn't just affect aesthetics or cost, it affects how a building handles load, resists movement, and endures over decades. The lessons these builders learned are rarely taught today, but they remain critical if timber is to perform as intended over time. Old-world builders sized beams based on wood behavior rather than rigid formulas. Timber is a living material and it behaves differently depending on species, cut, season, and environment. Historical carpenters recognized that beams don't fail merely from load. They fail from uneven stress, movement over time, and the cumulative effects of moisture. Beam sizing, therefore, wasn't just about span length or cross-sectional area. It was about anticipating these behaviors. The width, depth, and orientation of each beam were selected with a deep understanding of how the wood would shrink, bend, and settle. Modern building codes assume uniform properties for standardized species, but real wood is rarely uniform. Ignoring these differences compromises long-term performance. The rule of proportionality was more than a rough guide, it was practical science. Old builders followed ratios that adjusted depth and width relative to span length, load, and timber species. For example, a pine beam spanning 20 feet in a hall would be sized differently from an oak beam in the same span, not because of arbitrary preference, but because pine and oak respond differently to moisture, load, and creep. These ratios accounted for weight distribution, expected movement, and even seasonal expansion. Modern codes often substitute fixed calculations, which can lead to beams that are technically sufficient on paper, but insufficient in practice for long-term structural stability. Depth was often prioritized over width for long spans. Carpenters understood that increasing depth significantly improves a beam's bending strength. This principle is well known today in theory, but its practical implications were applied with far more nuance. Old-world builders increased depth selectively based on load paths and potential deflection. They would avoid simply increasing width indiscriminately, which adds weight and can introduce uneven stress across supports. Depth interacts with wood's fiber orientation, moisture content, and seasonal movement. Over decades, the right depth mitigates sagging, cracking, and joint failure without requiring reinforcement that disrupts natural timber behavior. Support spacing influenced sizing more than maximum load tables suggested. Historical builders considered the entire structural system, not isolated elements. Beam size was calculated in relation to post spacing, floorboards, roof trusses, and wall dynamics. Modern codes tend to treat beams in isolation, which simplifies calculation but ignores cumulative effects of differential movement. When timber shrinks or expands unevenly, unsupported spans react unpredictably, sometimes causing deflection or failure that could have been prevented with slightly larger beams or closer supports. Moisture content at installation was factored into sizing decisions. Old carpenters never assumed that wood would remain dimensionally stable immediately after felling or drying. Timber shrinks as it equilibrates with ambient humidity. Builders accounted for this by sizing beams to tolerate expected shrinkage without compromising structural integrity. A beam cut to code dimensions without considering moisture changes may appear correct initially, but can warp, cup, or twist over time. Historical sizing often included a buffer to accommodate these natural adjustments. Grain orientation and defects were, absolutely integral to sizing. Beam dimensions weren't determined purely mathematically. They also considered the material itself. Knots, slope of grain, and tension wood influenced how a beam would perform. A beam with a single large knot required greater depth to compensate, while straighter, denser timber could span further without adjustment. Modern codes largely ignore these nuances, treating all boards of a species as equivalent. The Old World approach recognized that timber is inconsistent, and sizing must adapt to each piece. Seasonal movement was, expected and accommodated in beam design. Historical builders anticipated that wood would move with humidity and temperature changes. Instead of forcing rigid conformity, they designed beams and joints to tolerate movement without compromising strength. This principle influenced sizing decisions, particularly in floors and roofs. A beam that is just large enough to carry the load may crack or twist if it cannot move freely. Slightly oversized or proportionally deeper beams accommodate this movement, preserving structural integrity over decades. Old World beam sizing improved longevity through redundancy. Beyond load-bearing, proportional sizing created a margin of safety for unforeseen stresses. Heavy snow, shifts in foundation, or partial moisture exposure could strain timber beyond its expected load. Modern engineering often sacrifices timber behavior for efficiency. While we cannot fully replicate Old World methods in every modern setting, appreciating their reasoning offers practical benefits. Recognizing that depth, species moisture, grain, and support spacing all interact allows builders to make informed choices rather than blindly following tables. Even slight adjustments, deeper beams for softer woods, wider spacing for stiffer species, allowances for shrinkage, can extend the life of a building considerably. Timber is a living material, and sizing is the first step in respecting it. Old World carpenters understood that wood is not inert. Every cut, every dimension, and every joint anticipates its natural behavior. Correct beam sizing doesn't just prevent immediate failure, it controls long-term performance, stability, and resilience. Modern codes offer guidance, but they cannot replicate centuries of observational insight. Knowledge of these historical practices bridges that gap. Studying the past ensures stronger structures today. The beam sizing rule that old builders followed wasn't arbitrary. It was the result of careful observation, repeated trials, and long-term evaluation of what endured. Timber that is correctly sized for its species, grain, and expected movement carries loads quietly, resists deformation, and survives generations. Ignoring these lessons risks structural compromise even if codes are met. For those who want to deepen their understanding of wood behavior, structural longevity, and historical practice, subscribing to the In the Beginning email list provides continued access to detailed research, step-by-step woodworking projects, and exclusive insights into timber that are not found elsewhere. Studying how old builders size their beams teaches us that respecting the material is just as important as adhering to codes. It is how structures are made to endure.